So the first thing we want to do is determine the domain and find all points of discontinuity. So we just want to figure out where is this continuous, where is it not continuous. Second, we want to find the intercepts of the graph. We want to find where it crosses the x and y axis. Those are oftentimes of interest. Next, I can determine the asymptotes of the graph. So all three of these I can find without taking a derivative just yet. Next part of it is take the first derivative and the second derivative. Remember, the first derivative is going to tell us where the function is increasing or decreasing and where it has relative extrema. The second derivative is going to tell us where it's concave up, concave down, and points of inflection. And we're going to put all that information together to sketch the graph. Okay, so let's put it to work. So we're going to do this on the function f of x equals x squared over x squared minus 9. Alrighty, first things first, what does it say? Find all points of discontinuity. Find where this function lives. Okay, so first of all, we have a rational function. And to find points of discontinuity, remember, it's where we have division by 0 or roots of negative numbers. We do have division here. We've got x squared minus 9. So x squared minus 9 equals 0, and x squared equals 9, which implies x is going to be 3 and negative 3. These are our points of discontinuity. So we'll need to keep those in mind. Okay. Next is determine the intercepts. Intercepts. Let's go for the y-intercept. That's the easiest. Because when we intercept the y-axis, it means we haven't moved left or right, so it means x is 0. That would mean y equals 0 squared over 0 squared minus 9, which is 0 over negative 9, which is 0. So the y-intercept is 0, 0. Let's see if we've got any x-intercepts. That means we set the function equal to 0. We let y equal 0, because an x-intercept is a place where we cross the x-axis, and we don't move up or down, so y is 0. Well, remember, we have a fraction. Fraction is equal to 0 exactly when its numerator is equal to 0. So that would mean when x squared is equal to 0, which would mean when x is 0. So the x and y-intercept are at the same place, 0, 0. Okay, step 3, asymptotes. So remember, we have vertical and horizontal. So let's go with vertical first. Those are the easiest. There's very little analysis that needs to be done. So remember, vertical asymptotes occur where the denominator is 0. So that's where x squared minus 9 is 0, which implies, as we know from above, 3 and negative 3. So we've got a couple of important pieces of information here. So first we've got an intercept, and we've got some vertical asymptotes. Okay. Now, horizontal asymptotes. Okay, we want to look at the limit as x goes to infinity of x squared for x squared minus 9. And remember, the focus here is as x gets very, very large, what really matters is our leading terms, x squared over x squared. We simplify that, get 1, and now, since that has no dependence on x any longer, that's what this limit is equal to. Okay, so we have y equals 1 is a horizontal asymptote in the positive direction, and we can also check to see if we have one in the negative direction. And we in fact do. Again, we only pay attention to the leading terms, and it is also 1. So y equals 1 is our horizontal asymptote in both directions. All right, so we've got intercept, we got points of discontinuity, which in fact turned out to be our vertical asymptotes, and then we've got a horizontal asymptote. Okay, now get to work on our derivatives. So, first derivative. Okay, bottom d top. Bottom, top, minus top, bottom, all over bottom squared. Okay, so we get x squared times 2x, that's 2x cubed, minus 18x, minus 2x cubed, over x squared minus 9 quantity squared. We can cancel off the 2x cubes, and we're left with negative 18x over x squared minus 9 squared. While we're at it, we might as well go ahead and find out where that is 0 and undefined. So it's 0 when the numerator is 0 and undefined, and the denominator is 0. So this will, we're finding our critical numbers, in fact, here. So this would, in fact, be when x equals 0, and this would be when x squared was 9, when x is 3 or negative 3. Well, those are points of discontinuity, so they can't be critical numbers. So I have a critical number here at x equals 0. All right, let's go ahead and find f double prime. Okay, bottom, the top, minus top, the bottom, all over bottom squared. So x squared minus 9 squared would be to the 4th power. All right. Now, what I'm going to do here is instead of multiplying all this out, I'm going to pull out common factors. So notice I have a common factor of an x squared minus 9. I can also factor out a negative 18. I'm going to pull out a negative 18 and a factor of x squared minus 9. What will that leave behind in the numerator? Okay, so let's take it one piece at a time. The x squared minus 9 squared times negative 18. Well, I only took out one factor of x squared minus 9, and I have 2 in that first term, so that leaves 1 x squared minus 9, and I took out the negative 18, right? Okay, now let's go minus, took out the negative 18, so that's gone, and then I got 2 times x times 2x, that's 4x squared, and I took out the factor of x squared minus 9, so that's what's left behind. All over x squared minus 9 to the 4th. Now I can go ahead and cancel one of those factors. This is equal to negative 18 times, let's see, I got x squared minus 4x squared. That's negative 3x squared minus 9 all over x squared minus 9 cubed. Okay. Alrighty, so now I want to do the analysis on this one. So what I want to do is similar to what I just did above, and that is determine where the numerator is 0 and where the denominator is 0. So I want to analyze when f double prime is 0. Well, that's when the numerator is 0. And I want to analyze where f double prime is undefined. And that would be where the denominator is 0. Again, what are we going to get here for the denominator is 0? X is 3 and negative 3. Can't be a point of inflection because those are where we have our vertical asymptote. So that leaves this left side here where the numerator is 0. Well, negative 18 can't be equal to 0, so that would leave negative 3x squared minus 9, 0, which would mean negative 3x squared is equal to positive 9, or in other words, x squared is equal to negative 3, and that is not possible in the real numbers. So we have no points of inflection, so keep that in mind. Okay, so let's see if we can put all this together. This is the tricky part, is we're going to go ahead and do our chart to help us determine where we're increasing, decreasing, have relative extrema, concave up, concave down. We already determined there's no points of inflection because we don't even have any candidates for them. Okay, so let's go ahead and do our chart. This is going to be one big chart. Okay. So what we're going to do here is, let's see, what important numbers do we have? We have 3 and negative 3, and we have 0, right? 0 is our candidate for a possible relative extrema. That's our critical number. And 3 and negative 3 are our vertical asymptotes. So those are the three values we want to include in here. So I'm going to make lines for negative 3, 0, and 3. All right, so now I want to analyze what's going on here with our function. So first I want to analyze f prime. So I want test value, sine, increasing, decreasing. And I want to test f double prime, and that's sine, test value, sine, and this time concave up, concave down. Put in our intervals. So negative infinity to negative 3, test values say negative 4. I can choose both for both f prime and f double prime. Between negative 3 and 0, negative 1 would be a good choice. Between 0 and 3, 1 would be a good choice. And between 3 and infinity, I'm going to pick 4. All right. So f prime, let's recall what f prime looks like. So if we take a look at this, x squared minus 9 squared, since it's squared in the denominator, that denominator is always going to be positive. So I really only need to pay attention to the sign of the numerator. Okay? So negative 4, negative 18 times negative 4, that would be positive. It would be increasing on this particular interval. Same thing for negative 1, negative 18 times negative 1, that's positive, still increasing. Okay, if I plug in positive 1, negative 18 times positive 1 is negative. It'd be decreasing. And then if I plug in 4, that's also going to be negative, decreasing. Okay, so now let's check concavity. And that I use the second derivative. So I'm going to remind myself what the second derivative looks like. Now this one, we don't have the luxury of having something squared. So I'm going to have to be careful when doing my analysis here. So I'm going to use my calculator. Okay, I get 2.99, so that would be positive, and concave up. I redo that and change the negative 4 to a negative 1. I get negative 0.42. Now it's concave down. Okay, let's change this to positive 1. I get negative 0.42 again, concave down. I change the 1 to a 4, 2.99, so positive, concave up, so it looks like that. All right, well, let's see here. Let's put this all together. Okay, let me draw on my axes. Okay, we should always label axes. Okay, where our units are, and we should label at least 1/2 of each axis. We know what the scale is. Okay. All right, so what do we have? Let's use, what do we got here? We've got an intercept, so I'm going to plot that at 0, 0. That's also going to be possibly one of our relative maxes and mins, and in fact, so at 0, we did change from increasing to decreasing there, right? Okay, we did change from increasing to decreasing, so that will be a relative maximum at x equals 0, so let's keep that in mind. All right. What else do we have? We have vertical asymptotes. We have them at 3 and at negative 3. We also have a horizontal asymptote at y equals 1. All right. So as we do our analysis here, we've got, let's see, increasing from left to right. And we could actually pick a few values if you would like to. It would be 1.3, 1 1/3. So 3, 4, 5, 6. It would be right about there. Okay. So we know our graph passes through that point. We also know we have a horizontal asymptote at y equals 1. So as we go out toward negative infinity, that's going to flatten out to positive 1. We also know from our analysis of our vertical asymptote, we could take a look at it. We've got a vertical asymptote at 3. And in fact, as we approach negative 3 from the left, we're going to go to the ceiling. And we can do a similar analysis over here on the other side. Choose positive 6. Okay, negative 6 and positive 6 are going to give us about the same value. This is a symmetric function. And again, we knew we have a horizontal asymptote, so it's going to flatten out as I go off to the right. And my vertical asymptote here at positive 3. And now what's going on in the middle here? What's going on in the middle? Let's take a look at our graph that we did, our chart. We can see that we are increasing up to the point 0, 0, and then decreasing after 0, 0. We also notice that to the left of 0, we're concave down. To the right of 0, we're concave down. We'll also notice to the left of negative 3, we're concave up according to our chart. And to the right of positive 3, I'm sorry, did I say to the left of negative 3, we're concave up. And to the right of positive 3, we're concave up. So we can put together all that information to sketch out this graph.